Are you responsible for specifying fire protection for an aircraft hangar, a warehouse, or any number of applications or processes involving Class B flammable liquids or Class A materials? Then you'll want to take a very close look at a proven method that provides another dimension to foam fire protection. High expansion foam systems from Ansell. While low expansion foam systems are often specified for the protection of most two-dimensional flammable liquid fires, high expansion foam is typically specified when the hazard has the potential for three-dimensional fires, where water supplies are limited, where excessive liquid runoff will not be tolerated, or where confined spaces could prevent firefighters from reaching the fire using conventional methods. Essentially, the difference between high and low expansion foam is defined by expansion ratio, which simply indicates the amount of foam solution needed to generate a volume of finished foam. For example, an 8-to-1 expansion ratio means that 100 gallons of foam water solution can produce up to 800 gallons of finished foam. Low expansion foams have expansion ratios ranging from 2-to-1 to 20-to-1. Medium expansion foams range from 20-to-1 to 200-to-1. While the ratios for high expansion foams range from 200-to-1 to approximately 1,000-to-1. The typical high expansion foam system consists of four major components: JetX high expansion foam agent, a bladder tank sized to fit the application, a foam proportioner, and one or more high expansion generators. The basic system operates solely on water pressure. Water enters the tank inlet where it surrounds the internal bladder. The pressure forces the JetX foam concentrate through perforated tubes to the tank outlet where it's routed to the proportioner. Simultaneously, water is directed to the proportioner at the same pressure as the foam concentrate. The Venturi effect of the proportioner mixes the foam concentrate and water, creating a 2.75% foam solution, or 2.75 gallons of concentrate to 97.25 gallons of water. The foam solution is routed from the proportioner outlet to one or more high expansion generators located in the hazard area. Within the foam generator, rotating nozzles spray the solution onto a perforated screen in a circular pattern. Simultaneously, the water-driven fan blows a high volume of air onto the same screen, producing the expanded foam. This expanded foam extinguishes fire in four ways. It carries water to the fire, where it drains out of the foam and cools the fire, the hazard, and the surrounding area. The low surface tension of the draining solution penetrates Class A materials and reaches deep-seated fires. It smothers the fire by reducing the air supply to the fire. And finally, it provides an insulating barrier around exposed materials or structures to help prevent the fire from spreading. It does all of these things using substantially less water and foam concentrate. Just one JetX 15 foam generator can produce a volume of expanded foam at a rate of nearly 20,000 cubic feet per minute, depending on inlet pressure. While most foams can only be used for two-dimensional hazards, the high volume output of high expansion foam systems enable both local application and total flooding protection. In fact, because of their unique capabilities, the National Fire Protection Association established Standard 11A specifically for medium and high expansion foam systems. NFPA 11A Chapter 2 covers total flooding systems for areas like warehouses, tunnels, mines, storage buildings, basements, ship's holds, and engine rooms, and other enclosed areas. The basic concept of total flooding is to fill the space protected to a level above the highest fire hazard. Specifically, if the fire hazard is under 20 feet, The space must be filled to a minimum of 2 feet above that hazard. When the highest hazard is over 20 feet, the space must be filled to 1.1 times the hazard height. A series of simple calculations are performed to determine various system requirements, like foam agent quantity, bladder tank size and type, type and size of proportioner, size and quantity of foam generators, discharge flow rate, and minimum operating time. The calculations are based on a number of variables: type of hazard, building construction, presence of a sprinkler system, normal foam shrinkage, and potential foam leakage, and whether outside air or inside air would be used to expand the foam. To determine the viability of using total flooding high-expansion foam systems for their rack storage warehouses, Sherwin-Williams asked Ansell to run full-scale fire tests at the Ansell Fire Technology Center. The 17-foot-high storage racks were assembled in Ansell's large indoor test facility and stocked with corrugated cases containing 720 gallons of mineral spirits in 1-gallon F-style plastic containers, representing a Class A combustible and Class B flammable liquid fire hazard. The test required 2 JetX 15A high-expansion generators with a total foam output of approximately 35,000 cubic feet per minute, based on an inlet pressure of 75 psi and using outside air. The objective was to have total product submergence in less than 2 minutes. Because of the dangers of running fuel fires, this is actually 1 minute lower than the standard requires. The flammable materials were ignited and allowed to pre-burn for approximately 100 seconds before the system was actuated. This is well beyond the normal reaction time a typical UVIR fire detection system would normally take to detect the fire and actuate the foam system. A few seconds after the system actuated, the foam generators began to discharge high-expansion foam. Notice how this dangerous running spill is immediately contained from spreading. Within 15 seconds, the foam blanket has reached the involved area. Within approximately 3 minutes, the foam has reached its required design level containing the fire. After approximately 9 minutes, the system has totally flooded the building to a level of 50 feet. With the test completed, the expanded foam is left in the closed storage facility for a soaking period, which is typically 60 minutes for non-sprinkled areas or 30 minutes for sprinkled areas. Afterwards, the door is opened and the foam is allowed to dissipate. After a thorough inspection of the stock, it is determined that about 1/3 of the plastic containers were saved. Saving any product is a great achievement with an intense fire like this, but the key success of this test was that the fire was immediately contained and the high-expansion foam prevented the fire from spreading beyond the rack to other areas of the facility. The high-expansion system used only 65 gallons of foam concentrate and 2,300 gallons of water in 8 minutes of continuous discharge. The test was determined to be highly successful by all parties involved. Chapter 3 of NFPA 11A covers local application systems typically used in aircraft hangars, for LNG spills, and for other hazards that have potential for three-dimensional fires. When protecting Group 1 and Group 2 aircraft hangars, NFPA Standard 409 must also be referenced for hazard-specific requirements and options. Military installations have their own protection requirements. Statewide Fire Protection recently installed an Ansell high-expansion foam system in the Imperial Air Hangar in Las Vegas, Nevada. The Imperial Air Hangar is a Group 1 facility measuring 42,000 square feet. According to NFPA 409, the supplementary high-expansion foam system has to fill the aircraft's storage and maintenance floor area to a level of 3 feet within 1 minute. The system also required a sufficient supply of foam solution to continuously operate the system for 12 minutes. A directly connected reserve supply of foam equal to the main supply is also required in NFPA 409. Based on the size of the hangar, the submergence volume was determined to be 126,000 cubic feet. In addition to the discharge duration and presence of sprinklers, normal foam shrinkage and 20% for the use of inside air must be factored into the total system output requirements. With 75 psi available at each generator inlet, the system required 11 JetX foam generators. The total foam concentrate required to supply 11 generators for 12 minutes was 605 gallons per system. With the requirement for a reserve system, 2 700-gallon bladder tanks with 8-inch proportioners were supplied. The total water requirement for the generators, overhead water sprinklers, and the handline nozzles totaled 2,565 gallons per minute. In comparison, a low-expansion foam system would have required approximately 6,840 gallons per minute. With both tanks filled and all preliminary testing completed, it was time to run the test. Within seconds of operation, the first generator kicks into action. And soon, all 11 generators are discharging foam, with a total output of approximately 192,000 cubic feet per minute. Within 1 minute, the system has filled the service area to the 3-foot level as required by NFPA 409. Successful tests like these, coupled with lower installation costs, no containment requirements, and the use of inside air, can explain why the United States Air Force recommends high-expansion foam systems for military hangar protection. NFPA 11A Chapter 4 provides guidelines when medium and high-expansion foams are applied manually using a portable foam generator, or special air aspirating nozzles commonly connected to the foam solution supply. The unique capabilities of high-expansion foam systems provide the versatility to protect various fire hazards, especially when the hazard is three-dimensional. The next time you find yourself specifying a low-expansion foam system, consider adding a dimension of protection. High-expansion foam technology. From Ansel,